This is the Daily Space for today, Monday, September 22nd, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. For fans of geometry-based holidays, happy equinox. Today, the sun passes straight overhead at the equinox as it makes its way south. With spring coming to Australia, South America, Africa, and points in between, we here in the north are seeing the first hints of fall. This is your regular reminder that the reason for the weather seasons is geometry. Turning to the news, we'd like to start things out by making invisible objects a little easier to find. In astronomy, one of our more annoying struggles has come from trying to figure out which objects are stellar mass black holes and which are neutron stars. While we know stellar mass black holes should exist, saying with certainty that any one particular object is a black hole and not a neutron star has been a challenge. Both these objects represent the end stage of a massive star's life. Stars that end with less than about 3.5 solar masses after experiencing mass loss, both as a star and, well, through explosion as a supernova. They end up as a neutron star, an extremely dense object about the diameter of Manhattan Island that is made largely of neutrons in a matrix. These objects do have surfaces and in some cases will undergo dramatic novae activity as material building up on their surface or in a disk around them periodically undergoes nuclear explosions. Objects that end up with more than about 3.5 solar masses, they end up as black holes. This happens because at this mass, neutrons can't repel one another and they crush together into some state we can't explain. No one really knows what goes on within a black hole. What we do know is that a black hole is so small that any surface it may have is within a radius from which you have to go faster than light to escape. Yes, folks, the defining factor in making something a black hole is that its escape velocity is greater than the speed of light. And since nothing can go faster than the speed of light, whatever is going on at the possible surface of a black hole is beyond our ability to see or presently understand. While the physics of neutron stars and the smallest black holes are very different, they are nevertheless super hard to distinguish observationally. In binary star systems, we detect both neutron stars and black holes from how they pull on companion stars and from the interactions they have with their surroundings. In many cases, we can't directly see either the black hole or the neutron star. What we see instead are X-rays from the material they are consuming. In new research published in the monthly notices of the Royal Astronomical Society with first author Srimanta Banerjee, researchers look at the X-rays from a large selection of sources they think they can identify as neutron stars or black holes, and they look to see if there's any defining characteristics that may separate the neutron stars from the black holes. They find that black holes appear to shift the spectrum of the X-rays with their gravity, causing two different populations to stand out. This means that we should be able to look at other systems where the geometry doesn't allow us to accurately measure the compact object's mass and say based on X-rays whether the object is more likely a black hole or a neutron star. This is the first diagnostic we've had other than mass to differentiate these objects. A remarkable amount of astronomy depends on being able to find objects with companions that allow us to get, well, insight into other characteristics. And it turns out a remarkable amount of astronomical phenomena are due to objects with companions that define their characteristics. One of the harder to explain objects in the sky are planetary nebulae. These expanding clouds of gas are often structured in ways that are hard to understand. These nebulae arise when sun-like stars die and exhale their outer atmospheres. How this process leads to sometimes square-looking concentric gas patterns, sometimes distorted patterns, and sometimes beautiful bubbles? Well, figuring that out was part of the justification to fund the Hubble Space Telescope. But even that telescope's great optics weren't up to the challenge. It turns out the Atacama Large Millimeter Array was needed to study the wind morphology in 14 planetary nebulae. By looking at the structure of the winds, researchers were able to conclude that a binary star, well, that can explain what we're seeing. According to the press release, the researchers estimate that the binary stars' changing influence on the wind, the way these two stars interact, that shapes the nebula. As the primary star evolves, the wind increases and the separation between the stars grows. And the researchers report they can successfully explain the various nebular morphologies we see using this evolutionary framework. In their model, different shapes are driven by different geometries between the stars, different masses, and evolutionary stages. With so many variables that can change, we can get, well, a seemingly infinite combination of structures. And that's what we see, a seemingly endless combination of structures. You can read about this work in the latest issue of Science in a paper with first author Michael Funk. Even the interactions between small objects, it seems, can drive appearances to change in wild ways. And I'm not just talking stellar objects. In the journal Nature Astronomy, there are two different papers looking at the same weird feature of two different asteroids, Bennu and Ryugu. Both these asteroids are essentially rubble piles. And while their compositions differ, they are both primarily composed of dark rubble that includes minerals that either include water in their structure or formed in the presence of water. Sprinkled atop both these asteroids are compositionally different bright objects, bright boulders that are from something that was hot and dry. In the Bennu-related paper, first author Daniela Dell'Agustina discusses using OSIRIS-REx's visible and infrared spectrometer to study these boulders' compositions. The team behind this paper discovered that the appearance of these boulders appears consistent with the mineral proxine, which is common on Vesta and Vestoids. Vestoids are small asteroids chipped off Vesta during past impacts. According to co-author Hannah Kaplan, our leading hypothesis is that Bennu inherited this material from its parent asteroid after a Vestoid, a fragment from Vesta, struck the parent. Then when the parent asteroid was catastrophically disrupted, a portion of its debris accumulated under its own gravity into Bennu, including some of the proxine from Vesta. Let me put this another way. Once upon a time, a reasonably large asteroid was minding its own business as it orbited the solar system, and it was struck by a chunk of Vesta that stuck. At some later date, an even larger object hit this asteroid, breaking it into the myriad pieces we see today. This means Bennu is a mix of some parent object, some Vestoid that hit that parent object, and additionally, at least one more object responsible for Bennu's shattered nature. The solar system is a rough place to be. The team looking at Ryugu was using the Hayabusa 2, which has a different suite of instruments that allow different kinds of explorations to be done. Using Hayabusa 2's spectrometer, researcher Eri Tutsimi is able to say that Ryugu is considered a C-type or carbonaceous asteroid, meaning it's primarily composed of rock that contains a lot of carbon and water. As expected, most of the surface boulders are also C-type. However, there are a large number of S-type or silicous rocks as well. These are silicate-rich rocks that lack water-rich minerals and are more often found in the inner rather than the outer solar system. While this isn't as definitive as saying bits of Vesta are on Ryugu as well, it is still the same story of impact after impact, adding new minerals while destroying previous structures. For us here on Earth, this has mostly worked out okay. The dinosaurs were destroyed by one iridium-carrying asteroid, but most of the asteroid strikes have left us intact. Nevertheless, this is a reminder that we need to keep looking up and looking out for that object looking to mess up our world. This has been the Daily Space.